Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just ask that you bless our work today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. I guess I should give you guys a quiz before I forget. Let's see here. Oh, come on. Tell me I got no markers. Oh, man. Do I have no marker? Yeah. Oh, yeah, you're fine. Okay. You're welcome. All right. I don't mind at all. All right. Quiz. Find first 3 theorems centered about x equals to 3 for f of x equal to e to the x. And that's all I got in this marker, so that's going to have to be the quiz. You have 3 minutes. That's how long it takes me to get my markers. So. One minute remains. Tick tock, tick tock. You guys excited about the weekend? I'm not. I've got an algebra test to grade. There's no telling what awaits me there. If I seem very depressed Monday, you'll know why. All right, enough suffering. Let's turn them in. Put your name on there. So are you thinking of the math major? You're going to come here for the math major? Oh. You're done with school?
Not school, math.
Done with math. Hey, I'm right here. No one ever rejoices being done with reading. Why are people so gleeful to be done with math? Thanks, everybody. All right, let's look at this. I won't look at these. I won't look. You're Your secret is safe. Listen, there's like 2 different ways to do this. I'll do the Taylor's theorem way to start with, okay? So f of x, right, is going to be equal to f of 3 plus f prime of 3 times x minus 3 plus 1/2 f prime prime of 3 times x minus 3 quantity squared plus dot dot dot. So you could do it this way. And that's pretty easy, right? Because what is the nth derivative of x here? It's just e to the x again, right? So this is just straight up e to the 3 plus e to the 3 times x minus 3 plus 1/2 e to the 3 times x minus 3 squared plus dot dot dot, right? And so there's the answer. There's the first 3 terms. That's solution number 1. So solution number 1 is just by Taylor's theorem, all right, which I'll prove for you, well, sort of prove for you in just a second here. I'm not sure I'll really give you, I'm going to sketch the proof. I won't take so much of your time as to really prove it. But anyway, I'll show you why it's true. So solution 2, the other way I would do this is with my adding 0 trick. So f of x is equal to e to the x minus 3 plus 3, right? So that's by laws of exponents e to the 3 times e to the x minus 3. And then I can use substitution. See, that's e to the 3 times 1 plus parentheses x minus 3 plus 1/2 x minus 3 squared plus dot 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 dot. And there you go. Another way to get the answer. And I even have e to the 3 factored out as a natural byproduct of my trick. You could ask the question, which is the right solution? How many feel like the solution in black is the right solution? Show of hands. Okay. How many people feel like the solution in blue is the right solution? Show of hands. How many people think this question doesn't make any sense? Show of hands. Very good. All right, that's what I was looking for. Yeah, I mean, it doesn't matter. You can go either way. So, all right, so something I've been neglecting, but I should take a minute or two to talk to you guys about is the statement and proof of Taylor's theorem, or more specifically, what I'm really proving is the existence of Lagrange's estimate on the form of the remainder. So here it is. See if I can turn off the lights up here. Yay! Haha. All right, so if you've got a function that has k derivatives on a closed interval I that has endpoints a and b, all right, then the kth Taylor polynomial, which is this, all right, plus the remainder term, the kth remainder term of b, is equal to f of b, all right. So this is just a definition. This is the kth Taylor polynomial evaluated at b, and that's just putting this here basically says that's whatever's left, right? So it's the remainder term. It's whatever is not covered by the kth order Taylor polynomial. Then there exists c in the interval such that the remainder term at b is given by the k plus 1th derivative evaluated at c divided by k plus 1 factorial times b minus a to the k plus 1. And so this is the theorem, all right? So basically, the way we use Taylor's theorem is just kind of in a sloppy way. What we've been doing is we've been assuming for functions that we're interested in, this remainder piece we can ignore. If we take the limit as k goes to infinity, that goes to 0, and we have an exact accounting for the function as generated by the Taylor series. That is, we are assuming that the function's analytic. In other words, that the Taylor series generates the function at the point in question. Anyway, here's the proof of this theorem. Excuse me. There's a different proof in your book based on integration. So the proof I'm showing you here is a twist on the mean value theorem. So here it is. Since the kth derivative exists on I, it follows that the jth derivative is continuous for j equals 1 to k minus 1, all right? And so we can define this number m, all right? I'm going to define m in a kind of crazy way. M is the number for which this equality holds true. It makes sense that you can do this because we can calculate the function at b, we can calculate the function at a, and we can calculate all these derivatives, right? So there's nothing stopping me from defining m by this equation. You could say, that's weird, and I would say, fine, but there it is. I defined it, so you have to deal with it. All right, our goal then is to produce a c such that the kth derivative at c is equal to this m, all right? If I can do that, that basically proves what I'm after, which is that the f of b is this kth Taylor polynomial plus this remainder term, all right? So, so to do this, it helps to study an associated function. We study g. So g is basically built from, I subtract this to the other side, minus, so look at this. It's like putting this equation up here equal to 0 and plugging in t for most of the b, for most of the a's, right? See that? So here's f of t, f prime of t, and so forth. That's the pattern. And then there's that m over here. Anyway, this is a function. You can define it. What else can we say about this function? It's continuous because it's built from the function and the derivatives of the function, which we know exist and are continuous because we've assumed so. And so we can study this function. Now, what's the deal with this function? What happens when you plug in t equals to a? What happens with t equals to a? Anything? I don't know.
0.
It's 0? How can you see that it's 0? I think you're right, but why is it 0? So if you plug in 0 into t, you get all of this stuff, right? So in other words, you get basically everything here with t replaced with a, right? Which is what? It's exactly all of this, right? And then you get minus f of b. So it's exactly the fact that rearranging this with minus f of b plus all this stuff is equal to 0. That's synonymous with this function having a 0 when you plug in t equals to a. All right? It's a little bit hard to see, but it's true. When you plug in a, you get 0 here. What happens when you plug in b? Well, that's easier to see, right? F of b minus f of b, 0. And then all of these things, 0, 0, zeros all around, right? B minus b is 0. So we've got a function which is continuous, which is differentiable, and which is 0 at a and at b. Now, this is going to be a blast from the past for you guys, but there's this thing called Rolle's theorem, right? Which states what? Basically, it says what comes up must come down, right? If the initial and final position of something is 0, right, then there has to be some place in the motion where the velocity is 0. That's Rolle's theorem. So there has to be a point between a and b such that g prime of 0 is 0. And so by Rolle's theorem, I get the existence of a c, excuse me, such that g prime of c is 0. Now what I got to do is take advantage of that data. So to do that, I have to differentiate my g. And differentiating g is a pain. But after you do it, and I can't look at this, so let's get through it. After you do it and do the steps, it works out to the kth derivative at t minus m times this stuff, right? So if you plug in c equals to 0 here, g prime of c is 0. What's that say? It says that you've got this non-zero thing, right? Because c is not equal to b. It's something between a and b. It's not b itself. So this is a non-zero thing. And then this, so that has to be 0. If the product of two things is 0, then this, and one of them non-zero, this must be 0. But this being 0 is tantamount to saying that the kth derivative of f evaluated at c is equal to m, which is what we set out to prove. And so there you go. That's Lagrange's form of the remainder. Now, the way we use this is a little bit sneakier. So basically, you don't actually want to find the c that makes it happen. What we usually want to do is find a bound on like that higher derivative. So if we can say that the higher derivative is smaller than something, that allows us to squeeze that remainder term to 0, basically, or at least to make it as small as we like. Let me show you. Any questions about this? I'm not going to put it on your test or anything. I just think it's important for you to see it. What you're looking at here is basically just a generalization of the proof of the mean value theorem. If you study that proof, you'll see that what I've done is I've taken the place where we use the secant line in the mean value theorem proof, and I've replaced it with the kth Taylor polynomial instead. But it's really just that, and it's not my proof either. It's from, I mean, it's a slight variation of something I found in Robert Ashe's book. But okay, so consider f of x equals to e to the x. All right, on j, and let's say j is I don't know, minus a to a, right? So we can look at what's the kth Taylor polynomial of x. It would just be what we were just doing this a second ago here. N equals 0 to k, let's say k minus 1, I guess, of x to the k over k factorial, right? So that plus what? That's tk, right? But we also have f of x equal to e to the x. Well, that's equal to tk of x plus what? Plus the kth remainder of x, right? Now, what does Lagrange's theorem say? It's a form of the remainder. It says that Rk of x is what? Rk of x is what is it? It's equal to, how's it go? Oh man, I put it away. It's supposedly equal to, no, I've lost it. Yeah, so the kth derivative, right? At some c divided by k factorial times what? Times, well, I guess in this it would be a minus, I mean, I'm sorry, my notation here is a little bit screwy. Let's do a and b so that it's easier for you guys to follow, a and b. Okay, so b minus a to the, what is it? K, yeah. My theorem, I think I've got k here, so I've got k plus 1 down here. Do you guys want me to, I'm just going to stick with what I have on the board. You can go back and forth whether you want this to go to k or to k minus 1. I would count either correct on the test if I asked you about it, so don't sweat the
You did it k minus 1 because the theorem states that it would be k plus 1.
Well, what I just had on my notes goes to, I mean, if you want me to be consistent with what I just had on the notes, I should put a k here, right? And well, this should be an n. You guys, come on, guys. That should definitely be an n. And if I do that, that makes this a k plus 1, right? So I guess that's the one I actually had just projected. All right. So let's write this. This is actually equal to what? This is equal to e to the c, right, over k plus 1 factorial times b minus a to the k plus 1, right? So here's the thing. In order for me to say e to the x is actually equal to 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus dot 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 dot, right? In order for me to make that a equality, this requires what? This requires that the limit as k goes to infinity of Rk of x is equal to 0 for any x. This is a separate notion. Like, this is completely divorced from the kind of convergence we were talking about in previous classes, like the interval of convergence. That's a separate matter. All right? So you notice what I'm talking about here is, does the remainder go to 0? So I'm asking a more subtle question. I'm asking, does this series, this series, we have proved already by the ratio test that this series converges for any x. All right? The question is, does it converge to this function? But anyway, what I have on the board is pretty much enough to prove it, because if you look at this, just fix a particular value of b and a, what happens as k goes to infinity here? You've got b minus a, which is just any old number, all right, that you like. Make it as small or as big as you want, it doesn't matter. As k goes to infinity, what do we have? We've got like number to the k plus 1 power versus k plus 1 factorial. The factorial wins eventually, right? So you can do this argument for any interval a, b you like. And so since you can do this for an arbitrary interval, it follows that this limit is equal to 0 for all x in the reals. I do not test on this concept. I think it's too subtle for this course. All right? What I'll test on is, of course, the interval, like the interval of convergence material we went over before. That's reasonable. What I'm proving right now is, in fact, that e to the x is analytic. In other words, that the power series that we generate actually converges to the function. So anyway, I'll try to work my way around this issue by just saying something like, assume your function's analytic, find a power series for it, okay? So I free you of the task of proving that the remainder term goes to 0 over the appropriate domain. If that's okay with you guys. If you want me to spend a couple of days of class on this and really develop it more, we could do that. But I don't think I should, though. I think it's not healthy. So anyway, now that we got that out of our system, let us get back to the usual things. So just to recap, a power series is a function whose rule is pointwise defined by a series of power functions. So basically what we have is f of x is equal to a sum, n equals 0 to infinity of a sub n times x minus x naught to the n, right? This is a power series. And as we've discussed, if you have a power series, its domain is very boring, right? It's either all of the reals, it's the center, or it's one of those 4 wacky choices, either both ends included, one end included, left end included, right end not included, right end included, left end not included, or both ends not included, either the open, the closed, or half open. Sometimes people will say the half open one, there's either clopen or opposed, but this is stupid. But anyway, so once you have this formula for defining your function, that says that the function's a power series. All right, the coefficients are a sub n, right? Wow, So then the second idea is that if we're given a function, let's say g of x, then we may reproduce the function locally by a power series expansion if g of x is analytic at x naught. So, and then how do we do that? Well, g of x is going to be equal to, and this is Taylor's theorem, sum n equals 0 to infinity, the nth derivative of g at x naught over n factorial times x minus x naught to the n. So for example, we could look at g of x equal to, 1 over 1 minus x. And 1 over 1 minus x, what's the graph look like? Vertical asymptote at x equals to 1, right? So what I mean locally is I mean g of x, this function I'm giving you, that's defined for all x except for 1, right? Where would the Maclaurin series, when we say Maclaurin series, we're talking about a series where centered at 0, right? And so we can find the Maclaurin series for this, right? So, I don't know what, this is actually 1 at 0, isn't it? I'll do the function in black, I guess. Oh, man. Oh, man. Come on. It's an asymptote. Shouldn't get there. So there's y equals g of x in black, right? Let's find the Maclaurin expansion for this. How do we do it? This is equal to what? This is equal to 1 plus x squared plus dot, 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 right? Because this is a geometric series with radius x and a equals to 1, right? So that expression I just wrote here is only locally producing g. It only produces g of x like up in here, basically. Only here, only in this particular arc, right? There's only this particular segment of the domain from 1 to minus 1. So this is good approximation. Well, it's not an approximation. It's a good representation, I should say. Let me just of g of x for the absolute value of x less than 1, aka minus 1 to 1. For this same function, I can reproduce it. I can represent the function by a power series, a different power series somewhere else, right? Like on the other side of the asymptote, I could represent this function by a power series centered at, say, 2, right? So like over here at 2, if I want to find the power series at 2, which is going to be good from like 2 to 3, I think we can kind of anticipate that, right? So it's going to model the function like up in here. How would I find that? Well, here's how I would do it. I would create an x minus 2 in the expression so I can make a substitution. So this is 1 over, let's see here, 1 minus parentheses x minus 2 plus 2, like that. So why did I do that? Because I'm trying to create an x minus 2 kind of series, right? So let's see here. Can you guys help me out with this? What happens then? Clean it up a little bit. This is really, if I put, I guess minus 1 minus x minus 2, right? But that's still not quite the right pattern. We're always looking for a over 1 minus r, right? This is sort of our goal. Because once we're there, we're geometric, right? So how do I make that minus 1 become a 1? What do I do? Yeah, just like factor out the minus. If you want, I'm going to bring it upstairs. Minus 1 over 1 plus x minus 2. So that's minus the sum, n equals 0 to infinity, of minus x minus 2, parentheses to the n. Let me clean that up. What we have is we've got the sum n equals 0 to infinity, minus 1 to the n plus 1, times x minus 2 to the power n. Or if you want me to expand on that, it's, let's see, n equals 0 gives me a minus 1, and then I get plus x minus 2, and then I get minus x minus 2 squared, and then I get plus x minus 2 cubed, and so forth. So here's a different, so this represents g of x near x equals to 2. What's in green represents g of x near x equal to 0, right? So if you have a function who has some kind of rule which is globally defined, right, then it can be the case that one power series will represent the function one place, and a different power series will represent the function somewhere else. All right, so the notion of a power series is kind of a local idea. It gives you a local picture of the function. Just like first semester, we use tangent lines to approximate functions, right? And that's a local notion. Like that tangent line's only a good approximation to the function near the point of tangency, but might not be good elsewhere. Yeah, go ahead.
I was wondering if you could do a series expansion for sin x.
Yeah, sure. Yeah, so this is my spiel for today. The rest of the time it's homework problems for you guys. So whatever you want to ask me, go for it. So you said sine. Oh my goodness. I think I'm doing better, but still. You know, there were 4 days I had no cough. I was better. I was really better. And then I got a totally new cold. So just for the record, I haven't been sick for 2 months. It's been like I was sick for a month. I was better for 4 days. And then I got sick again. It's very different. It's very different. What was your question?
Series expansion for sin x.
A series expansion for sin x. But okay, but just that?
How did you get the formula for the series from sin x?
Oh, okay. So to start with, I suppose I would use Taylor's theorem, right? So if I have f of x equal to sin x, then f prime of x is what? Cosine x. F prime prime of x is negative sine x. F prime 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 of x is minus cosine x. The fourth derivative is, sine. The fifth derivative, well, anyway. So you can kind of see where we're going with this. You see the pattern start to repeat, don't you? See, we're back to here again, right? So I could state this. I could tell you that if I look at the 4jth derivative at x, I just get what? If I look at the 4j plus 1th at x, I get what? The 4j plus 2th, x equals to what? What's the 4j plus third derivative of x is equal to what? I mean, this is the pattern. So like, this is 4 times 0. This one is 4 times 1. So this guy is like 4 times 0 plus 1. This is 4 times 0 plus 2. This is 4 times 0 plus 3. This down here would be 4 times 1 plus 1. So what I'm trying to get at here is the 0th term and the 4th derivative term, those are just sine x, right? Whereas the j plus 1 is cosine. The, j plus 2th is minus sine. The j plus third is what? Minus cosine again. Those are all your derivatives. So what I'm trying to get at here is if you think about all possible whole numbers, they're divided up into 4 big buckets. Multiples of 4, 0, 4, 8, 12, 16, so forth. Then multiples of 4 plus 1, like 1, 5, 9, 13, 17, right? Or 2, 6, 10, 14, right? And so all of the whole numbers fall into one of these four categories. And so when I write Taylor's theorem, which says what? F of x, which is sine x in this case, right, is equal to a sum n equals 0 to infinity of the nth derivative at a over n factorial times x minus a. I assume you want me to find the expansion at a, am I right? I mean, if we do this at 0, the story gets a little bit simpler, because if we do it at 0, like the 4j and the 4j plus 2 terms just drop out, right? Because sine of 0 is 0. But this, you got all four of these cases, right? So the way I would do that is just to break this excuse me, into the two sums. So this is equal to, come on, marker, sum j equals 0 to infinity of the, let's see here, we've got sine of a, I don't know if this marker is going to work, sine of a over 4, oh man, I can't, I'm sorry, this marker is just, come on. It's a new marker, it should work. All right, it's starting to have, give it a second here. I've learned that you should do this with a cap on. Ooh, I think I may have gotten a little carried away there. Sum j equals 0 to infinity. And so, oh man. What was I saying? Oops. All right. Anyway, so you got sine of a over 4j factorial x minus a to the 4j, right? And then this is a horrible way to do this. I'm sorry. I mean, I can do it, but do I want to do it this way? I'm not enjoying this. I mean, what I'd have to do then is to plug in a into these and put them down here. I mean, that's what would be needed. Let me show you how I usually do this. Tell you what, I will suffer this calculation in the case a equals 0, just to make good on it. Let's do that. So let's put a equals to 0. In that case, this is just two things, right? The sum j equals 0 to infinity, cosine of 0 over 4j plus 1, factorial x to the 4j plus 1 plus the sum j equals 0 to infinity minus cosine of 0 over 4j plus 3 factorial x to the 4j plus 3. And it just so happens that if you combine those terms, what you get is the sum k equals 0 to infinity minus 1 to the power k over 2k plus 1 factorial x to the 2k plus 1. So merging both of these into one grand glorious sum, you get that. So like the when k is odd, these are the k odd terms, and these are the k even terms. I don't know why this does not usually seem so complicated to me. I don't know what I've done. I'm sorry. But anyway, yeah.
Would that be the Maclaurin series of sine?
Yeah, this is the Maclaurin series of sine, right? Yeah. So, I don't know. I guess using this idea here probably wasn't that helpful to us. Let me show you how I do it at A. Usually what I would do is this. I would just say, okay, so sine of x. Once I have this, right? And we've worked this out previously, and I think when I worked it out before, it didn't seem so complicated. I don't know what it is about what I'm doing today makes it seem complicated. Just to me, anyway, it does. But anyway, sine of x. So what I do is I just subtract a and add a. All right? And if I do that, that gives me sine of x minus a cosine of a plus the sine of a times the cosine of x minus a by the adding angles formula. Right? And so that gives me cosine of a times the sum k equals 0 to infinity minus 1 to the power k over 2k plus 1 factorial times x minus a to the 2k plus 1 plus sine of a sum k equals 0 to infinity. So now I'm putting the power series for cosine, which is minus 1 to the k, over 2k factorial x minus a to the 2k. And so there you go. That's actually the answer to the question you asked me. I think you asked me at the start of this, which is what's the power series for sine expanded about a. That's what it is. That's how I like to do it. I find direct implementation of Taylor's theorem here unavoidably complicated. I mean, it's quite awful, right? Because all four of these derivatives is contributing non-trivially. But then you also have to see that like this and this are lumping together and that are lumping together, right? Because, I mean, in the case, for example, a equals to 0, still both of these come together into one thing. Yeah. Yep. I'm sorry? Is there a general formula? What are you asking? Or are you stating?
Just sine x plus k pi over 2, then you just plug it in. It's more simple.
I'm not sure what you're saying.
I think he's asking if you have like sine like x plus 2, could you just like plug that into the expansion to find the to use that as well?
Well, yeah, if we're asked to find the expansion of the sine of x plus 2, then I would just make a substitution of x plus 2 into the known sine series. I'm not sure.
It's, I mean, the derivative of x, like the nth derivative of x is sine x plus k pi. Right? The k derivative of sine x is sine x plus k pi over 2.
Oh.
That one.
I see. No, I have not thought about it that way. That's interesting. So you're saying just to turn everything into sines, just with the appropriate augmented argument. So let's see here. What did you say the formula was? You said the kth derivative of x is what? It's sine of what? X plus k pi over 2 is what you see. Definitely works for 0. Let's see here. Is it legitimate when k equals to 1? Sine of x plus pi over 2 is sine of x times cosine of... no, it's sine of pi over 2 plus cosine x. Yeah, that's right. Sine of x plus pi is minus sine x. Yeah. Yeah, cool. Very nice. So if you see this, then you can do this also, right? So this works in all 4 cases. And then you could, or maybe I should say n in my notation at the moment, right? But then still, you're going to have to sort through, when you plug in a here, that it gets you 4 different things, right? I mean, at some point or another, you have to face the music, which is that the 4 different derivatives give you 4 different values, which then get regrouped into 2 values to get this. Or if you wanted to leave it ugly, you could leave it as the sum of 4 sums of 4plicities, like a 4j term, a 4j plus 1 term, a 4j plus 2 term, a 4j plus 3 term. You could. There are other problems like that, where the power series, you can't nicely combine the 4j plus 1 and the 4j plus 3 term. It just happens that the 4j plus 1 and the 4j plus 3 terms have a nice pattern that allows you to combine them. There are uglier problems where you don't have such a... What's that? Yes. Well, power series are absolutely convergent on the open interval of their domain of convergence. So yeah, we can rearrange at our pleasure. Yes. Other questions? Do you guys have easier questions for me? Finding the power series expansion for sine about an arbitrary point is, it's kind of a tough problem. All right, well, you guys have a weekend. Think about your problems. Bring them back to me Monday. All right? Thanks.